Thank you very much. I should mention, this is joint work with Troels Henriksen and Cosmin Oansir, also from University of Copenhagen. And today, we are going to talk about this APL on GPUs using a tool chain of first compiling APL into an intermediate language, and then later compiling that intermediate language into yet another language, and then compiling that language into OpenCL code, which can then be executed on compiled and executed on GPUs. So we're giving here a progress report, and we're also going to demo a little bit of how we envision this can work with some machine learning. We still have some work to do to get very good performance here, but at least we can show that I think we are in the right direction to some extent. So let me just give a little bit of motivation first. The goal here is, of course, to provide this high performance at fingertips of domain experts. And the reason that APL is particularly useful here, also as a way of exploring possibilities, is that it has these powerful and concise notations for array operations. And that means that we can deal with data in bulk. And also that the APL programs are inherently parallel, and they're not just parallel, but also data parallel. At least many of the primitives are. And then, of course, there are lots of APL code around, as you know. And some of that code is looking to run faster. The challenge, of course, is that APL here is dynamically typed, and we need some kind of, to generate efficient code, we need some kind of type inference, and we need to be able to resolve many of these primitives at compile time. And some of the complications arise from functions being rank polymorphic, that the built-in operators are highly overloaded, and also we kind of need some kind of subtyping as in many contexts 0 and 1 are used for booleans, and in other contexts they are really integers, and yet other contexts they are doubles or floats. So this is some of the things that we will have to deal with. And the approach here is to kind of have an inference approach where we will not allow, we basically want to infer from the program invariants that the programs can use. For instance, that this particular variable is ever only going to be containing integers or booleans and so on. So that using that information we can then generate efficient code. And this is a very different approach than an interpreter will take, where of course you will optimize have some special cases, but you will branch out in the particular code for the idiom, and then at runtime take the good path. So this algorithm that we have implemented is basically compiling this APL, processing the APL code, and then generating these tail programs. And tail is a typed array intermediate language. So let me say a little bit about what features are supported here. We usually code up, we have to kind of not take the entire dialog front end and support that. So what we have focused on is to say, well, if programmers really write using these dynamic function syntax, then you can actually do a lot. So that means that you can write up things like an else operator here. You can use trains also to write the mean in this style. And we also support various kind of scalar extensions, identity item resolution, overloading resolution, and so on. There are some limitations here, of course, once we take this approach. Static scoping and static rank inference. We basically need to be able to infer ranks at compile time. And we also have only very limited support for nested arrays. This is something that we'll need to dive more into to actually get some, make it a little bit more easier for the programmer to write algorithms, as we'll see. And then we take this whole program compilation approach. So we basically assume that the whole program is available, which means that for very large APL programs, this is probably not suitable, but maybe one can pick out the kernels that needs to run fast. And of course, no execute here, since we have a static approach. So the tail language, this typed array intermediate language, really has a formal treatment to it. So which is kind of, we wanted to be able to reason in isolation about the internals and the backends, and isolate that from the front end, the APL idiomatic programming and all the variants of the operators and so on. So we basically wrote down what do we want to support at the intermediate language level, and then we wrote up these static types that basically identifies and specifies what should be the behavior, to some extent specify the behavior of the operations and also their limitations. So just to take one example here, you have a rotate, which is basically this version that takes an integer, and then it takes an array, and it returns an array of the same form. And this is just one example, and then you can write these up. You also have a dynamic, a static type system for the system, so that we can check once we generate the code, does the intermediate language program actually type check? And that has caused a lot of bugs. Once you're in the compiler itself, having that treatment that you actually try to type check your program at all points for any program that comes through this tool chain. And then of course also it has a small step reduction semantics, so that we really can specify what does this operator mean. And that has helped us in debugging and understanding, implementing the back end and so on, separating the concerns here from the compilation into tail, from the generation of Futhark code or any other high performance backend. So here's a small example, and here we have in APL the mean and the standard deviation, the variance written up, and then this is compiled into tail, and then there's also an interpreter, so you can basically evaluate this thing. You wouldn't write your program in this language, of course, but this is a way also to understand, okay, what is really, and you can optimize on this language itself. And a lot of optimizations happen at this level also, I should say. It can say type check okay and evaluates, and it returns this array here. So this is just something about the tail language. A little bit more, how do we deal with all the primitives? So looking up in the literature, there are lots of primitives, a definition of primitives available. And for instance, here's one from Guevas and Wyatt in the POPL 78 paper, where you basically define the inner product here as something working on arbitrary ranks. So that means that we can basically specialize this code for each. So we really have a prelude which looks like this, and then when that is compiled and the dot here is used, and we'll see it here. And of course, we also have a real dot punctuation just bound to this one, but this is just to demonstrate that the user himself can also write this. And then you can have an operator taking plus and multiply here, and dot here, and then the two arguments A and B. And then it will generate this code. It will actually first generate something quite a lot more complicated, and then we'll shrink the code to specialize it to this code, and then that can be evaluated and run. So this is how we deal with many of the primitives. And then of course, for this particular work, we are trying to look at how to compile this typed array intermediate language into a language called Futhark, which has been developed in particular by Troels, who's sitting over here, as part of his PhD thesis on generating high-performance GPU code from a functional language, a data parallel functional language. And that, of course, gave some liberty because the definition of the language could also evolve over time. And the language supports is a pure functional language with second-order parallel array constructs like reduce and map and scans and so on. And then it supports some imperative-like language constructs to iterate computations. So it's a sequentializing compiler. It tries to basically make whenever there's an excessive amount of parallelism, it tries to actually see where is it important that we sequentialize code. And maybe it's at the outer level you want to sequentialize, and the inner level you want to have code running in parallel, or it's the other way around. So that depends very much on, and there are lots of transformations here at that level. So the language is quite similar. So here's some, I won't go into detail, but you can write and some simple functions adding 2 to every element of a vector. And you can see here they are specially typed here. This is an integer vector. And down here we see an integer matrix here. And then you can compose functions in a good way. Lots of optimizations are happening. Loop fusion is important, and then there's an attempt to flatten all the nested parallelism appearing here. So and that we have quite good benchmarks showing that works quite well. And although it's not fully general, then in many cases it does quite well with the flattening. Okay, so it also does other things like optimizing for coalesced memory accesses on GPUs and so on. So here's another example, making an integral here, compile into tail first, and then into Futhark code before optimizations. And then once that's dealt with, we can basically get code to run on the GPU by using the Futhark compiler. Instead. So that's it. So I'll just give you shortly some benchmarks here, showing that it actually runs for these compute-bound examples, like some signal processing. There's also something calculating the date of Easter for quite a few times. The integral example, as we saw before, and then some Black-Scholes financial calculation of option prices. So here for these very compute-bound things, we see that on this particular architecture, it's an 800 times speed up on compared to a sequential hand-written C implementation on a similar priced hardware, so to speak. What else here? For stencils, which are not quite compute-bound, we'll see here also speed-ups, but not as good as we saw before. This is using live, where you extend it a little bit, since we don't have support for, it's not the one-liner, and that's due to the case that we don't have nested arrays, so we need to kind of do some tricks here just to rotate the matrices individual. First you rotate, and then rotate the other in the column-wise, and then you have this usual condition down here, and you can then repeat that. And for Mandelbrot, I also just want to mention, it was shown last year as well. These are the same examples here. That this is a idiomatic version of Mandelbrot, where you get 11 times speed up. If you want to invest a little bit more to obtain some inner sequentialization, instead of processing the entire map at each time, then you can, for each pixel instead, you are basically have a sequential loop inside. That can be implemented with this version, also staying within APL, but it takes a lot more, quite a little bit more code, and then you can get quite a lot of speed up. Okay, so just a little bit of some features, what happened since last year. So, for instance, we have now a complex number support. So now we can do, Mandelbrot in one line. People are probably used to see this kind of implementation. This corresponds very closely to the slower version of the two Mandelbrot examples, where you're basically you're processing the entire matrix 9 times here in this example. Then we have some efficient parallel segmented reductions. There's a paper by Troels and a student on FHPC 17 on treatment of segmented reductions and how that can be implemented on GPU. So here we have 2 different cases, and the trick is here to get both of these to run efficiently. Here we basically have a lot of segments, and here we have fewer segments, but each of them are larger. And to be able to deal with these and parallelize those on GPUs requires some special tricks. And that we see can be useful for some APL programs where you actually have these patterns. There are also lots of Futhark components being developed over the last year that we can also use in the APL programming, random number generators, Sobel sequences, and so on. So we hope to link to this linear algebra routines and so on. And then many Futhark internal optimizations. So now I want to just show an effort at trying to say, okay, what if we want to try to use this for real? Not really real, but for some larger example. So I took up the challenge of trying to do some work on digit recognition. So there's a large data set called MNIST, which contains a lot of images, 28 times 28, and then they are classified into the particular digit that they should map to. And the idea here is to have a neural network with 3 layers, and then use backpropagation to use the training set here to teach the neural network to recognize these digits. And it's like it is organized so that you have 3 layers here. There's an input layer, and then a hidden layer, and then the output layer. And basically, the input layer corresponds to all the pixels, which are each pixel is a float with the intensity. And then the hidden layer has these 30 sigmoid neurons with randomized weights initialized to random weights here and biases. And then the output layer here has only 10 neurons here. So we can see here that once you feed in an image here, if the network knows about how to recognize digits, then if it's an 8 that comes in, then the 8 here will have a high number to the output, and then we can read that thing to identify that was actually an 8 coming out. I'll return to that here, and I'll just give you some APL snippets of the code here. And again, how we write the code here is basically just to say, well, we want to use the dynamic function notation to write all the functions here. So here's a sigmoid function, quite simple, written up in APL. This is a function that looks like this. So the idea is that basically it is continuous and differentiable, and that allows us to implement the backpropagation. This is a key thing recognized in the machine learning, or neural network at least, that you can use the sigmoid function and this backpropagation to teach the network. And then I'll just put here some how will we write these interpreting the. First of all, we need to convert a digit into its unit vector. So this can be done, of course. Also, predicting a digit would be probably something that would look reasonable to an APL programmer, but it's quite different than what you do if you're writing a C program because here, of course, you're doing a vectorized things with multiply and stuff like that. So this is to predict the image here. If you have a vector like this, let's just go for the entire here. So you insert an image here. Hopefully people can agree that this looks like a 9. But maybe the neural network will say, well, it could also be, there's some chance that it's maybe a 3 or even a 0, right? But 9 has a larger. This is a larger of the activations here. So that means that we will interpret this network to say, well, this is a 9. And this is how we basically feed forward on the net. So if we provide this image, you basically write it like this. And this is where it's a little bit ugly. We would like to have a better notation for dealing with structured arguments and giving them names and so on sometimes, because it can look a little bit difficult to read if you're, of course, to APL program. This is probably reasonable. But you see these alphas and omegas around here, of course. But the feed forward here is basically taking one layer and feeding that layer, the input to that layer to the next layer, and then we will see here we repeat this process twice, since we have a 3-layer network with 2 layers containing neurons. So this is basically how, and you see a matrix vector multiplication happening here, and then you're adding the bias, and then you're having the sigmoid function on the entire vector here. So this is how it is implemented. That's pretty straightforward. So the overall approach would be to use something called stochastic gradient descent, and this is really some Python code that I then attempted to port. And first I did it in Futhark, and the written here is a pseudocode and I won't go into detail about the exact backpropagation algorithm, but what I will say is that the idea is to have you have the data set, the training data, you random permute it, and these epochs are the number of times that you process the entire data set. You random permute the training data, then you divide it into batches using the split thing, and then you compute the backpropagation on each of these batches. And that can in principle be done in parallel, and this is what the Futhark implementation does. And then it will result in a number of nablas, or changes to the suggested changes to the network that will allow it to teach better the next time around. So this is what is called stochastic gradient descent, since we are shuffling around the random permuting the training data, and then we are then taking a subset of those and then updating the network. And this is how we just initialize the network, and then we run for these epoch times using the power operator here sequentially at the outer level, and this could potentially be parallel. The APL version that we implemented was doing this in sequentially. And what we could see here that we do get speed ups in the Futhark implementation compared to the sequential compiler, Futhark compiler, which runs with this performance. It compiles into C, and then the OpenCL backend here that has quite a at least some better, 4 times better performance here, with various kinds of configurations of the network. And what we would really want is to have this working in APL. We would kind of need something kind of like a map function, where you not only you don't only use the each, you really want some kind of nested arrays here to allow you to map or to get things back that are more than just one set. These layers are really not regular. They have, the matrices are not of the same size, and that means that we need to process them in isolation. Either we can flat them out and process them like that. That would be one possibility, or we would need some kind of nested arrays to deal with it. And so currently, even though I was trying hard last night. We are still some way to for the APL. It runs and it works, but it's very slow. As we can see here, it's 20 times slowdown. And I guess we just need to spend more time. This is currently 400 lines of APL code, and there are some unnecessary reshapes here and there that definitely needs to go away. It would be very interesting to see how this thing would work, and I didn't try it out, although it should actually be working in Dyalog' APL. But all this thing about reading the images and stuff is the hard part for me. And dealing with the Dyalog' APL interpreter in general. But this would be very interesting to see whether how this benchmark would run, whether you would write it in a different style to actually hit peak performance in the interpreter. And then I just want to show here at the end, there's some interoperability demos that we can do. We showed them last year. This is all still working well, and there's some work on integration. Lots of related work. Of course, in this area in particular, I should of course mention the Aaron Souzier work on that you've probably heard about, and there's also been I think a working class where you could actually try it out. Yeah. So and we would of course like to collaborate on finding out what subset should we support and so on. Yes. More real-world benchmarks are probably needed to see how can we deal with this wider subset of APL, and then we would like some kind of APL type annotations to allow us to basically specify some properties of the functions that we write, so that we can get a kind of more design by contract theme to programming with these dynamic functions. And so I think with that, I will love to hear if you have any questions of any kind, please. Thanks.
Yeah, I think we have time for one or two brief questions. No questions?
No.
Okay, well, thank you very much, Martin.
Okay.